Hello and welcome to another lecture on the topic of rate of change. We want to do some word problems here, some examples. It says let g of t, this g of t is just like f of x using function notation. G of t equals 400 times brackets 15 minus t all squared be the number of gallons of water in a cistern t minutes after an outlet pipe is opened. Find the average rate of change of drainage during the first 5 minutes. That's the average rate of change we want to calculate. So what we're going to say is very simple. We're going to say average rate of change of drainage is actually change in G divided by change in T. Change in the number of gallons of water divided by change in time, basically. And because it says during the first 5 minutes, so that means from t equals 0 up to t equals 5 minutes, we need to be considered. We need to consider. So if I write g sub 2 minus g sub 1 over t sub 2 minus t sub 1, if I use that notation, this is actually the drainage after 5 minutes minus the drainage after 0 minutes. And the denominator would be 5 minus 0 because it says during the first 5 minutes. During the first 5 minutes, it means from t equals 0 to t equals 5. So using the equation, we can substitute the numbers 400 times 10 squared. And you know how I got 10 because 15, I can show the work. 15 minus 5 is 10. I thought we don't need to show it, but 15 minus 5, okay, and then minus 400 times 15 minus 0 squared, basically, and divided by 5 minus 0. If you use your calculator, the answer would be negative 10,000, and the unit of measurement is obviously gallons per minute because the numerator is measured in gallons and the denominator is measured in minutes. So gallon per minute is the unit of measurement. So the average rate of change in the first 5 minutes is actually negative 10,000 gallons per minute. Now, what is the meaning of the negative sign? Like, when is the rate of change negative, when a rate of change is positive? Whenever a quantity is increasing in value, the rate of change is positive. Whenever a quantity is decreasing in value, then its rate of change is negative. Here we got a negative answer, so you should not think that you made a mistake. You didn't make a mistake. The reason why you ended up with a negative answer because the quantity, which is the volume of the water, is actually decreasing, okay? The number of gallons of water is decreasing, so that's why you end up with a negative rate of change. If somebody was pouring water into the tank, then in that case, the volume would be increasing and you would end up with a positive rate of change. But that is not the case here. Because these are word problems, I'm not going to write it, but you have to know that you have to write a final closing statement or a paraphrase in your own words for every single word problem, needless to say, of course. The population of bacteria in a sample is 250,000 at 1 p.m., 500,000 at 3 p.m., and 1 million at 5 p.m. Is the rate of change in the population between 1 p.m. and 5 p.m. constant? Yes or no? That's what we need to find. There is no equation in this exercise. As you see, there is no quadratic function given to us, so perhaps it was not even necessary. So I'm going to say delta P over delta T. I use letter P standing for population. I could have used delta Y or delta X, the traditional letters. Not that it's wrong, but P for population, T for time makes more sense. That's why we write delta P over delta T, but it's the same concept. And I can say this is P sub 2 minus P sub 1 over T sub 2 minus T sub 1. Now, I can find the rate of change between 1 p.m. and 3 p.m. So that will be 3 minus 1 in the denominator. And in the numerator, I would say 500,000 minus at 1 p.m. we had 250,000. So that will be 250,000 in the numerator and then divided by 2, because 3 minus 1 is 2. So this gives you 125,000, and the unit of measurement is bacteria, okay, bacteria in the numerator, divided by hour, so bacteria per hour. So this is the average rate of change between 1 p.m. and 3 p.m. Now we are going to calculate the same average rate of change, but this time instead of 1 p.m. to 3 p.m., we're going to find from 3 p.m. to 5 p.m. So the denominator, so I can say like P3 minus P2, and then T3 minus T2 if I use a different notation. So 5 minus 3, and then 1 million, I believe, was the number of bacteria. So 1 million, take away 500,000. Okay, so if you do the math, you get 500,000 divided by 2, which is 250,000 bacteria per hour. And you see that these two rates of change are not the same, obviously. So the answer to the question is no. The average rate of change is not constant. Okay, because if it was constant, then you should have had the same rate of change from 1 p.m. to 3 p.m. And the same rate from 3 p.m. to 5 p.m. You should have had exactly the same rate of change. But you see that the rate of change is different from 1 p.m. to 3 p.m. and from 3 p.m. to 5 p.m. One answer is 250,000 bacteria per hour. The other one is 125,000 bacteria per hour. So these two are not equal to one another. Therefore, we cannot say that the rate of change in the population was actually constant from 1 p.m. to 5 p.m. And the answer was no. So this was one example, but we didn't have any function. This one says the height of a model rocket in flight can be modeled by h of t, just like f of x, equals negative 4.9 t squared plus 25 t plus 2, where h is the height in meters and t is the time in seconds. Find the average rate of change of the model rocket's height during the second. Okay, so here we have an equation, so perhaps we can use the equation. So how are we going to write our formula? We have height versus time. It's not population versus time. So I'm going to write delta H over delta T. This is the average rate of change, okay? And delta H means change in height. Delta T means change in time. It says in the second. So in the first second starts from t equals 0 up to t equals 1. The second starts from t equals 1 and it ends at t equals 2. The third second starts from t equals 2, it goes all the way to t equals 3. The fourth second starts from t equals 3, it goes all the way to t equals 4, and so on and so forth. So it says during the second. So this means that we're talking about 2 minus 1. We're talking about from 1 second to 2 seconds. That's the length of the second basically. And in the numerator, we have h2 minus h1, which would be height at 2 minus height at 1, clearly. And here, the denominator is 1. Plug in 2 seconds for time. So 25 times 2 plus 2. This is actually h at 2. And then minus h at 1, which means we plug in 1 for time t. So we need a calculator to evaluate this expression, and the answer would be 10.3 meters per second. The numerator is measured in meters. That's the height of the model rocket, and the denominator is measured in seconds. It's time in seconds. So meters per second would be the unit of measurement for this rate of change. Why is it positive? Because the height of the model rocket is increasing. That's why it is positive. Now, perhaps if we wait for like 2, 3, 4, 5, 6 seconds pass by, this rocket is not going to go to the moon. Eventually, it's going to come back down. And if we calculate the rate of change at that time, we'll see the answer will be negative, which means that the height of the model rocket is decreasing. But right now, we have a positive answer. So we do know that during the second, from t equals 1 up to t equals 2 seconds, the height of the rocket was increasing. The quantity involved here is the height. It was increasing, and the rocket was ascending, actually. That's the conclusion. The circular area of a healing wound is given by A of r equals pi r squared, where r is the radius in centimeters. Find the average rate of change of the area when the radius decreases from 2 seconds to 1.9 seconds. Another question. Now, A of r is just like f of x, okay? It's just a function notation. And pi r squared, of course, it's a famous formula. That is the area of a circle. I believe you may remember that from many, many years ago. Okay, so we want to find the average rate of change of area this time. Average rate of change of the area when the radius decreases. So if you don't mind, I'm going to use letter A, capital A, representing area. P for population makes sense. H for height makes sense. A for area makes sense. For all of those, I could have just used delta y or delta x, but the thing is that it makes more sense to use those letters. Delta A over delta r, rate of change of area with respect to radius, not the time this time. So this is going to be pi r sub 2 squared minus pi r sub 1 squared divided by r sub 2 minus r sub 1. We can say we have pi times 1.9 squared. We plug in 2 for r sub 1. In the bottom, 1.9 minus 2. I don't write 2 minus 1.9 because initially it was 2. So the radius was 2. This is actually r sub 1, okay? And then later it decreases to r sub 2, which is 1.9 centimeters, right? So it wasn't going from 1.9 to 2. It was going from 2 to 1.1, actually. So r2 minus r1 would be negative in the denominator. If you do the math in the numerator and divide by the bottom, it's going to be 12.25. And the unit of measurement in the numerator is, of course, square centimeters. That's the unit of measurement for measuring area. And then in the denominator, we have radius that is measured in centimeters. So the unit would be centimeters squared over centimeters, or square centimeters per centimeter, in other words. You may say this is 12.25 centimeter by simplifying the unit, but it's better to leave it as square centimeter per centimeter so that it would show that this is rate of change of area with respect to radius. It is like much clearer that way. So we were supposed to find the average rate of change of the area when the radius decreases from 2 to 1.9, and we ended up with, of course, an answer which is 12.25. What else can we add here? I think, yeah, that's about it. From 2 seconds to 1.9 seconds. Okay, so we did all the calculations. Negative divided by negative is positive. And that's the rate of change of area with respect to radius. So wrapping up in this lecture, we did 4 different examples of how we calculate average rate of change between 2 points, okay? And in the next examples, or in the next lectures, I should say, I'll be giving you examples about how we estimate, how we find an approximate value, approximate answer for the instantaneous rate of change. Okay, that's what will be the next topic. So keep practicing and solve as many problems as you can. Thank you for your attention.